Good evening students, welcome back to BSc second year physics class. In last lecture we discussed about the electric field, magnetic field, electromagnetic field, electromagnetic spectra. If we move forward, the next point from the from third chapter is Ampere's circuital law. In this lecture we are going to understand what is Ampere's circuital law and how important is this law in electromagnetic theory. Well, it is a current distribution which help us to calculate a magnetic field. And yes, the Biot-Savart law does the same, but Ampere's law uses the case high symmetry. We will first understand the Ampere circuital law followed by its proof. So, let us begin. First, we will define Ampere circuital law. Ampere circuital law states that the line integral of a magnetic field forming a closed loop around the current I carrying wire in the plane normal to the current is equal to the mu naught times the net current passing throughout the closed loop. It means what? The line integral of a magnetic field over a closed loop is exactly equal to the mu naught times the current passing throughout the closed loop is nothing but a Ampere circuital law, where mu naught is the permeability of the space having value of 4 pi into 10 to the power of minus 15 n per a square. Actually, this law is based on assumptions that the closed loop consists of small elemental part of the length dl and the total magnetic field of the closed loop will be integral of magnetic field and length of these elements, line integral of magnetic field over a closed loop dl. This closed loop is called as Ampere's loop. Further, this integral will be equal to the multiplication of net current passing throughout this closed loop and the permeability of a free space. It means, once again, the line integral of a magnetic field over a closed loop dl is equal to the permeability of a free space times the current passing throughout the closed loop, mu naught times I. Okay. Now, after understanding the Ampere circuital law, we have to prove it. There is a small derivation for the Ampere circuital law that we have to discuss. First, we will prove Ampere circuital law for a regular coil, in which if we consider a Ampere's loop with radius r and current is flowing perpendicular to the plane of this loop, and if we consider dl is the small length element of that loop, we have to prove that line integral of b dl is equal to mu naught times I. Starting from the left hand side, we can see in the diagram the angle of the length element dl and magnetic field B is 0. dl and B is 0 because both are in same direction or both are parallel. Therefore, integral B dl is nothing but B dot dl means the dot product between B dl. It gives B dl cos theta. If cos 0, if theta is 0 means cos 0 is equal to 1. B integral dl. B integral dl. We know that magnetic field due to a long current carrying wire is B is equal to mu naught I by 2 pi r, where is 2 pi r is the circumference of that Ampere's loop. Also the integral of element will form the whole circle of circumference of 2 pi r. Therefore the integral dl is nothing but it gives 2 pi r. Integral dl is equal to 2 pi r. Therefore integration b dl is equal to mu naught, where b is nothing but mu naught I by 2 pi r, and integral dl is nothing but 2 pi r. The 2 pi r get cancelled. Therefore integral b dl is equal to mu naught times I. Hence we can prove that the line integral of a magnetic field over a closed loop dl is equal to the permeability times the current flowing throughout that loop for a regular coil. If we consider for irregular coil, the same case, but for irregular coil, integral b dl is equal to mu naught times I, starting from the left hand side, integral b dl1 is equal to mu naught times I by 2 pi r1 into dl1 Now from the diagram we can show that d theta 1 is equal to dl1 by r1. If we substitute that value, dl1 is equal to d theta 1 r1. Therefore it gives integral mu naught I 2 pi r1 into dl1, which is equal to mu naught I by 2 pi into d theta 1 because r1 into dl1 or dl1 is nothing but d theta 1 into r1. r1 from the numerator and from the denominator get cancelled, and d theta it gives 2 pi, a complete 360 degree. Therefore 2 pi get cancelled. Finally we get mu naught times I. For irregular coil also we are getting line integral of magnetic field over a closed loop dl is equal to mu naught times current flowing throughout that loop. Okay, in this way we can prove that Ampere circuital law for a regular as well as irregular coil. There are keynote of this Ampere circuital law. The above two derivations proves the magnetic field at a point does not depend on the shape of the Ampere's loop, Amperean loop. For symmetric as well as asymmetric derivations proves that magnetic field at a point does not depend on the shape of the Ampere's loop. Magnetic field is same at every point in the Ampere's loop. Magnetic field is same at every point in Ampere's loop. Magnetic field possesses cylindrical symmetry. Okay. The direction of magnetic field at any point on the Ampere's loop is tangential to the circle formed at that point, with wire passing throughout the center, and the direction could be calculated by right hand thumb rule, where on holding the current carrying wire such that the extended thumb shows the direction of current in the wire, then the curling of rest of the four fingers represent the direction of rotation of magnetic field. It means what? Here we are showing the direction of current, magnetic field and the length element. It totally depends on right hand thumb rule that we are describing with this third note. Once again, direction of magnetic field at any point on the Ampere's loop is tangential to the circle formed at the point with wire passing throughout the center, and the direction could be calculated by right hand thumb rule, where holding the current carrying wire such that the extended thumb shows the direction of the current in the wire. Then the curling of rest forefinger represent the direction of rotation of magnetic field. Okay, these are the keynote of a Ampere circuital law. Okay, any doubt in this Ampere circuital law? If you have, you can ask me anytime. It represents the line integral of a magnetic field over a closed loop. dl is equal to the permeability times the current flowing throughout that loop, mu naught times I. This is nothing but Ampere's circuital law. Thank you.